Okay, so guys, in this right here, this one that we're about to simplify, this cube root of 500, guys, first thing you're always going to ask yourself is, what's the index up here? And what index am I dealing with? Okay, so here's what we're going to do. You remember that table I talked about, that perfect nth root table? Okay, so here's kind of what we're looking at. You're going to jump into this cube root column right here, okay? Now, we're trying to simplify the cube root of 500, and I'll do some work up here on the board here, and then we'll write it down. But you guys kind of visualize this. Okay, I would start in my perfect cube column right here, all right? I want to start high and work myself down. So start big and work your way down, okay? What's the radicand right here? What value's underneath the root sign? Okay, so guys, right here, I see a 512 right here. You all agree with that? Okay, so I would start by working this right here and say, all right, let's take 512 and divide it by what value first? 512 is obviously not going to go into 500. Would you all agree with that? Okay, so let's see if 343 will go in there, right? Because isn't 343 the next perfect cube above 512? So if I pull this up, and maybe you could tell me right away, is 343 going to go into 500? No, not evenly at least, right? Okay, so we don't get a whole number there. Talk to me about the next one. What would be the next value I would check besides 343 to see if it goes into 500? Okay, so I'm going to go 500 and divide it by... Okay, now somebody tell me why I'm in this x cubed column again. Yeah, we've got an index of 3, so we've got to be in that cube root column. 216 go in there perfectly? Nah. So what should we try next? Anybody have any good feelings about 125? Like how many times? Okay, does 125 go into 500? Okay, so here's the deal here. We could write this cube root of 500 as a product of two cube roots. It could be the cube root of 125. How many times did 125 go into 500? Okay, now check it out, kids. When I go back to this table right here, do you see where the 125 was in that perfect cube column? Okay, go all the way over to the left, that x column right here. What's the x value that you would multiply 3 times to make that 125? 5. So therefore I could say, well, my friends, that cube root of 125 is something that we simplified from that expression up there. This would now become 5 times the cube root of what? Well, 5 times the cube root of 4. And this would be your solution right here. Okay. Guys okay with that? Okay, what if the index was 4 up there? Would you work with it? Which column would I have to jump into if the index was 4? Okay, so we'll be referring to that table a lot, okay? All right, I feel like this first one here, this one's pretty manageable, okay? This is probably one of these problems like, yeah, I'm pretty good with this, all right? This next problem that we're about to look at, oh my Lord, this is not easy, okay? This is kind of one of these, I don't know. All right, okay, all right. First things first, we've got some rules about simplifying radicals. I want to go back over to this on this first page. You don't need to go over there, okay? Guys, I'm going to highlight some things on the first page. Follow along with me. First of all, on the vocabulary on the first page, it says simplest form of a what, kids? Okay, there's 3 bullet points right here that I'm going to highlight. It says no radicands have perfect nth powers as factors other than 1. Okay. All right. So like that last one that we were just doing, 125 came out of 500, right? The fact that I could take a number bigger than 1 out of that 500, that was important. Okay. Next part right here. No radicands contain fractions. Okay. So there's no fractions underneath a radical side. This third one right here, this is the one I want to pay attention to. No radicals appear in the denominator of a fraction. Oh my gosh. Okay. Well, guys, let's take a look at what we're dealing with right here. Oops. In this example right here, don't you already have a square or some kind of a radical in the denominator? Is that good or is that bad? That's bad. Okay, so here's what we're going to start to do. We're going to do what we start calling rationalizing the denominator. Okay. And in this case right here, I'm going to rewrite this just like this, the fourth root of 19 over the fourth root of 4. Now, the first thing I would check is this. Since the indices are the same on each of those, the question becomes, will 4 go evenly into 19? Will 4 go evenly into 19? The answer is what? No. Now, had this been something like, I'll write this up here. Had this been maybe the fourth root of 20 over the fourth root of 4, okay, since the index is 4 here and the index is 4 here, what's 20 divided by 4? Will 4 go evenly into 20? We could have simply written this as the fourth root of what then? 5. That would have been nice, but we're not in that situation here, are we? No, because 4 won't go evenly into 19. So here's what we do. I'm like, okay, no problem. To rationalize this denominator, think about this. If I had the square root of 8 down here in the denominator, maybe I had a up here, and I said I need to rationalize that. I need to get rid of the square root. We would multiply by another square root of 8. But I have to do this in a form of 1. So if I multiply the bottom by the square root of 8, what do I have to multiply the top by, friends? Guys, what's the square root of 8 times the square root of 8? Yeah, because it becomes the square root of really what value? Yeah. So this would really be a times root 8 all over 8. Okay. What's the index up here, my friends? Okay, so it's like if I can put 2, if an index is 2 and I have 2 of these roots together, it just becomes an 8 down there. And there's no more radical down there. Well, the way to treat this is as follows. What's the index down here in the denominator, kids? So here's your best answer for this. Okay, now it turns out that this is quite an interesting problem right here. All right, but I'm going to teach you the way you could have gotten done right there. All right, but I'll tell you why here. But watch what I'm about to do. Guys, this section gets kind of difficult right here because number sense for some kids is difficult. All right. What I end up doing, guys, is if I've got an index of 4, to rationalize that down there, this really becomes the fourth root of 4 times the fourth root of 4 times the fourth root of 4 times the fourth root of 4. Guys, think about this. Could I multiply all these together since the index is the same on all these? Okay. So watch what happens in the bottom here. Put an equal sign out here for me. In the bottom, you're going to end up with the fourth root of something. Guys, help me with the math. 4 times 4 times another 4. 64. See how good we are. Times another 4. 256, right? Okay. Now think about this, kids. If the square root of 8, you don't need to write this down, times the square root of 8 was equal to 8. Okay, the index is 2, and I have 2 of these right here. What's the index on all of these? 4, and I have how many of these? Okay, there's 4 of them, and then that number underneath the radical sign, or your radicand, if you will, is what value in each one of these? Okay, check this out. If I go to my chart, go down to 4th power column. You see the 256 right there in the 4th power column? What's the fourth root of 256? Okay, do you guys kind of see what I did there? I'm like, okay, I've got a fourth root of 4 down here. I don't want any roots down here. So the way to get rid of that and make this just a 4 on the bottom is to say have 4 fourth roots of 4. Okay. Now, here's the deal. If I multiply the bottom by those fourth roots of 4, what do I have to do to the top to make sure that we maintain equality? It's fourth root of 4 everywhere, right? Okay. Y'all buying what I'm selling so far? Okay, so this is where things maybe get a little trickier. Because we're really multiplying by 1 every single time, aren't we? Okay, so this becomes the tricky part. We need to take 19 times how many 4s? Okay, so let's do that. 19 times 4 times 4 times 4. What do I get for a value up there? Okay, so that's the 4th root of, what was that number, guys? Did you see that? 1216. 1,216. Okay. All right. The good news is, guys, you already have what in the denominator? 4. And have you gotten rid of the radical sign in the denominator? Okay. By rules of simplifying rational or radical expressions, is that a good thing or a bad thing? That's a good thing, isn't it? Okay. Now, what we may need to do is simplify the 4th root of what else, kids? 1,216. Okay, let's see. Maybe that's a perfect 4th power value. Let's see. What column am I going to jump into? Column 4. I'm going to go all the way up to 1,216. So there's 1,296, right? So the first value I'm going to check is to see if 1,296 goes in there. It won't, because this is bigger than 1,216, isn't it? So what we need to do is to check and see if that value 1,216 is divisible by what first, kids? 625, right? Okay, so let's start checking. I'm going to go 1,216 divided by, what was it, 625? Okay, is that good or bad? That's an epic fail, right? All right, so we'll go 1,216 divided by what next? 256. Is that working for us? No. 1,216 divided by what next? Not working, is it? Okay, let's go 1,216 divided by what next? Slay. Yeah. What have we got? Do you all agree right here that I could write this top as, I'm running out of room up here a little bit. I'll squeeze this in here. The 4th root of, what value went in there? 16 times the 4th root of what? Okay, talk to me, friends. Of that value up there, 16 and 76, which one of those is a perfect 4th power? I'll go back to the table. Does 16 or 76 show up? 16 does. Okay, follow that 16 all the way to the left. What is the 4th root of 16? 2, right? Okay. So do you guys agree? And you guys talk to me about this right here. Do you agree that what we end up with here now, we're at 2 times the square root of, and I know I'm running, I'm sorry, not the square root. Which root do I need there, kids? What was our index on everything? So 2 times the 4th root of 76 all over what? Okay. Now speak to me in one more term. How about that part 2 over 4? One half. So the top, this could become a 1. This could become a 2. Solution here would be the 4th root of 76. We can't break that down anymore. Over what value, kids? 2. Wait a minute. Is Slay dead now because it's 2023? I can? You're not ready to cancel me yet? No, never. Yeah. Are you serious? I think the advisory only goes to noon over there, though. So maybe the roads will get better and maybe play. I wonder what their policy is over there. Well, here's the deal. Do you want to know something, Ava? I told the JV girls make sure they bring practice clothes because I was concerned about if they would have school or not up there today. So maybe you'll get a night off. Kids, I want to go back to this right here. Thanks for the update, Ava. I appreciate that. Go back to this right here. Guys, this is a very difficult example right here. Now, I alluded to the fact that we could have gotten away by multiplying by just 1/4 root of 4, because it turns out that the 4th root of 4 times the 4th root of 4 would have been the 4th root of 16 in the denominator. Some kids wouldn't catch that. So I just want to talk about this, my logic right here. If I had like the 3rd root of 5 down here, kids, in the denominator, and I had a up here, and I said, let's simplify this, okay? How many more 3rd roots of 5 would I have to multiply by to get rid of the radical signs down there? Well, the idea here is, what's the index, kids? 3. So how many 3rd roots of 5 would I need to really be able to rationalize the denominator easily? You would need how many more then? 2, because you've got one here already, right? Okay, so just to make sure you're following my logic on this, if I multiply the denominators by 3rd root of 5 and another 3rd root of 5, how many 3rd roots of 5 do you have on the bottom? So this would just be what in the end? Well, this would become the cube root of 125 if you did that. And you don't need to write this stuff down. And that would just make this a 5 down here, because the cube root of 125 is 5. And I'm sure that will come up a lot. So you might want to highlight or star that last example that we just did, okay? I'm going to be honest with you. If you can make sense out of what just happened there, you're going to be in pretty good shape, okay? All right. Guys, show of hands, first of all. Does everybody have everything down there? All good? Ready to move? Okay, example 4. Okay, writing a radical expression in simplest form. Okay, I'm going to make a little note right here. And my little note for this right here is to say, look at your denominator, kids. Okay, what is the denominator in this? You ever see a root something plus or minus some other whole value? I want you to think this word right here. Okay, think conjugates. Okay, so if I had a plus b, what's its conjugate? Absolutely, a minus b. So what we're going to do is we're going to multiply a form of 1. Whenever you have a denominator like this, in this case, you've got a root 7 minus 2. In order to rationalize this, or in other words, not have any radical signs down there, in order to get rid of the radicals with something like root 7 minus 2, we would have to multiply in the form of 1, where that form of 1 has the numerator and denominator as a conjugate of the original denominator. So if I look at this right here, kids, root 7 minus 2, what is the conjugate of root 7 minus 2? Okay, so I'm going to multiply in a form of 1, so I'm going to have root 7 plus 2 up top, and root 7 plus 2 in the bottom, okay? You guys agree the part that I just wrote in red there? You guys agree that that's really 1? Root 7 plus 2 over root 7 plus 2? Some number over the same exact number should be 1, unless we're talking about zeros, okay? All right, well, help me then. Guys, up top, let's do some multiplying, okay? What's 1 times root 7 plus 2? So the top is just going to stay what, kids? Okay. Favorite 4-letter F word in math? Thank you. FOIL. Okay. FOIL. Last night, Coach Driscoll before basketball games is always like, they come up with stuff like, if we were the Bobcats, we would say beat the Bobcats. The first word's got to be the same as their name. So beat the Bobcats. Robert goes, guess what he goes? They are the Falcons. And Ava Mills immediately started laughing like crazy and turned her back to the group. Right, Ava? Was that you or was that someone else that did? Was it you? Guys, root 7 times root 7. 7, right? Okay. Help me out, guys. Root 7 times positive 2. Very good, Hamed. 2 root 7. Okay, here's where things get interesting. We got to take negative 2 times everything. So negative 2 times root 7, friends. And then finally, negative 2 times positive 2. Okay, help me with my north of Highway 3 math skills, all right? The top is going to remain root 7 plus 2. But in the bottom, what are the 2 root 7s really going to do to each other, friends? They're gone, aren't they? What are you really left with in the denominator here? 7 minus 4 to become 3. Okay. Guys, here's the cool part. Do I have any radicals in the denominator? Any radicals in that denominator? No. Guess what? Simplified. Okay. So the thing that I'm going to tell you to look out for is this. Anytime you see something like root 7 plus something, or a root plus some whole number, or a root minus whole number, what do I want you to think, kids? Think conjugates, okay? And I'm also going to add to this. I want you to write think conjugates in the form of... Okay, so listen to what I say. If I multiply the bottom by one conjugate, I also have to keep the top balanced or equal by multiplying the top by the same conjugate. So I'm going to say think conjugates in the form of what value, really? 1, because isn't this part right here, root 7 plus 2 over root 7 plus 2, really equal to 1, isn't it? Okay. Guys, take a look at what you have in front of you right now on that page. What questions do you have for me so far? Wait, did Alexa say the weather's going to get bad here today?
I hope so. She definitely will. What? Ask her. Yeah, ask her if we're going to.
We will. We'll ask her at the end of the hour. Okay. All right. My question to you guys is this. Do you all have this down right now? Good? Guys good on the wall over there? Middle of the room good? This side of the room good? Okay. All right, let's move on. I think we're getting close. There's a lot to this, guys. We may not finish today, but we're going to, oh my gosh. Okay, I like this here. Things get a little easier right here. This is good, right? Okay. Guys, example 5 starts talking about adding and subtracting. The thing you need to underline or highlight right here, what's this? Like radicals and what else? Okay, think of this. This is kind of like combining like terms. So if I had something like this, if I had 3x squared plus 8x squared, you guys know enough to say, Parson, that's going to combine to what? 11x squared, okay? So guys, when we start talking about adding and subtracting like radicals and roots, those roots, in this case, the first example, the 6th root of 17, those are kind of like your like terms. So what I might do is this. I might just say, well, this 6th root of 17, that's a like term with that right there, okay? Guys, what we really have here is this. How many 6th root of 17s do I really have on the left over here? What value is really out in front of that 6th root of 17? Or what number times that? 1. How many of them do I have over here? 9. Okay, so how many 6th roots of 17 do I really have here if I'm adding 1 and 9 of them together? Okay, so this is just simply 10 times the 6th root of 17. Y'all good with that? Same game right here. 7 to the 1/3 power. That's a like. 7 to the 1/3. So how many 7 to the 1/3 do you have on the left? 5 of them. How many 7 to the 1/3 do you have on the right? You're multiplying them by 6, right? So this is really going to simplify to 11 times what? Okay, now you have to be careful on this because kids all the time will do this. They'll want to take this 5 times 7, okay? But guys, do you agree that that 5 is really like 5 to the 1st power? Right here, you guys agree that's like 5 to the 1st? You could multiply them together if the 1/3 matched an exponent right here of 1/3, but are these exponents the same right here? They're not, so don't multiply those together. Okay? First 2, you okay with those? Give me a yay or nay. Yay. All right. Okay, this last example, this one's not fun. Okay, this one not so much fun. First of all, guys, we've got the 4th root of 48 minus the 4th root of 3. Do those 4th roots even match to combine right now? Does the 48 and the 3 even match? No. Okay, so what we have to consider here then is some simplifying, okay? I'm going to put a little arrow to the 4th root of 48, and we're going to say we might have to simplify this to get some like roots. Okay, so guess what chart I'm going to? Okay, what column should I jump into for that fourth root of 48? Okay, looking at the fourth root of 48, 48 would fall between 16 and 81, wouldn't it? All agree with that? So 81's not even going to go in there. So we better check to see if what goes in there. Will it go in there? How many times does that go in there? 3. Okay, you're like, oh, 16 goes in there. You would say what? 3 times? So I could write this as the fourth root of 16 times the fourth root of 3 minus fourth root of 3. Okay, now something very interesting is going to happen here. Kids, as I go back to this chart right here, take a look at that 16. In which column am I right now? Okay, what is the fourth root of 16 according to our chart? 2, isn't it? Okay, so are you buying that I could write this as 2? That's that fourth root of 16 right here. That's a value of 2, isn't it? Wouldn't that be 2 fourth roots of 3? Really minus how many fourth roots of 3 is this over here? Well, it's really one of them, isn't it? Okay, check this out, guys. Doesn't this fourth root of 3 right here now match this fourth root of 3 right there? Oh, yeah, it does, doesn't it? So what's 2 of them minus 1 of them going to yield? 1. All right, so solution-wise, what am I looking at here? Fourth root of 3. Okay, that, my friends, is your solution. So, guys, just because they say, well, add, subtract, like radicals or roots right here, and you're like, well, Parson, the values for radicals, they don't even match. And I'm like, no problem. You might have to take one of those radicals and do what to it first. And when I simplified, didn't the fourth root of 3 match in the end then? Didn't the fourth root of 3's match with each one? So we had 2 of them on the left minus 1 of them on the right, left us with 1 in the end. Okay. All right, very good. Very good. Oh, this has been the best class of the year. Okay. Like anything else, sometimes I get going pretty quickly. Y'all know to slow me down if you don't get it right. Cool with that? Okay, talk to me, kids. Simplifying variable expressions. Okay. If I thought that there was an example that's maybe the most important in this, I think example 6 is this. Okay. This stuff, very important. And I don't know why that's in that last box, but don't worry about that. Okay. If I had to pick a part where I thought probably the most important part, it's this. Okay. Guys, here's a quick reminder. If I have the nth root of a right here, kids, we started this way at the very beginning. This is a to the 1 over n power like that. So as an example, if I had the third root of, let's go, 6, this would equal 6 to what power? Yep, so if the nth root of a implies a to the 1 over n power, then the third root of 6 would imply 6 to what power again? Okay. And we talked about that way at the very beginning of 4.1 when we were starting that, okay? So here's the deal. Guys, when we start dealing with stuff like this basically is what you're going to end up with here, okay? Couple different ways I can go about this. I'm going to make a little T-chart on this right here. You guys can choose which way you like to do this best, all right? First expression that we're trying to simplify is the cube root of 27d to the 12th, okay? I think the best way to do this is as follows. This 3 that's out here, I would make this into a fractional exponent of 1/3, okay? So I would take this radical and write it as a rational exponent. So I would call this 27d to the 12th. Yeah, maybe I don't want to do it this way. To the 1/3 power, like so. Okay. Okay, so what this really means, kids, is this. It means 27 to the 1/3 when I bring that in here and here. should be 27 to the 1/3 power. It looked like a 43, didn't it? What's 1/3 of 12 going to be? Okay. Now, the 1/3 exponent, you could type that in your calculator and say, what's 27 to the 1/3? And it would tell you. Another way to think about it is this is really the cube root of 27. What is the cube root of 27 going to get you? What times itself 3 times is 27? So this would be 3d to the 4th. Okay. So maybe I'm a droid at home. You guys don't have a droid? Like R2D2? Or BB-8? Mine's 3d to the 4th. Okay, now another way to do this is this. I could have called this the cube root of 27 times the cube root of d to the 12th. Okay, friends, think about this. Do you know the cube root of 27? 3, okay? And then this one right here, you're taking the cube root of d to the 12th. It's like, in this situation, it's like saying, well, how many times would 3 go into this 12 right here? 4 times. So really, the cube root of d to the 12th would be d to the 4th. Yeah, so you're good with that, okay? D to the 4th. Okay, do we get the same value either way? We do, don't we? Okay. All right, well, let's try the next one. Kind of the same concept. I'm going to go with the first way of writing this. So, guys, here's what I'm going to do. I have the 4th root of, I'm going to rewrite the whole thing again, x to the 4th over y to the 16th. Okay. This could equal, all right, I'm going to put parentheses here, x to the 4th over y to the 16th, all to what power, friends? If this index is 4 right here, what power could I write that to? How would I use a rational exponent to express an index of 4? It'd be to the 1/4 power, wouldn't it? Okay. Can I bring this 1/4 in here now? What's 1/4 of 4? So this would be x to the 1st up top, wouldn't it? I can bring the 1/4 to that exponent as well, which would make what in your denominator? What's 1/4 of 16, friends? Okay. Have I gotten rid of all radicals in the denominator? Is that a good thing or bad thing? Okay. Oh, is that wrong? Singing?
I put Ava and then Jamie in little letters.
There you go. How about I answer it?
Oh. That's a fancy animal. You guys, plus guys. Divided by What is that?
Oh, wait a minute. I don't like it that way. I'm going to do it this way, guys.
Yeah.
Radical sleigh. All right. Guys, I think this is the last example, isn't it? Nope. We still have another whole page.
No, just.
Oh my gosh.
That's what I'm saying.
Are you serial? Oh, lordy. Okay, no problem.
Okay.
You guys want... oh, boy. Okay. Guys. Y'all know who Gabriel Jesse is?
Yeah.
Very intelligent, right? Okay, I'm not trying to scare you, but even he questioned me about some of these here sometimes. I don't know. That was probably a bad idea, wasn't it? Okay. All right. There's really no rhyme or reason or magic to any of this right here, but the part is this. Okay. The thing you need to understand is this. I'm going to make 2 notes up here in example 7. In the end, you want no roots in the what? Okay, another note right here. You will not You will not want negative exponents in the end. So no. You don't want negative exponents in the end. All right. Okay, let's talk about this right here. Guys, when you start something like this, break it up. Okay, I'm trying to, first example, simplify cube root of 2, a to the 13th, b to the 3rd, c to the 8th. All right, hear my method of madness on this, all right? This is going to become the cube root of 2 times the cube root of a to the 13th times the cube root of, anybody want to guess? What's the last part? Okay. All I did is broke each part out. You all agree with that there? Okay. Simplifying stuff like this in simplest form is difficult for kids. But guys, I have a question. Go back to your elementary days. When you did division in elementary days, simple division, like 8 divided by 3, you would say, how many times would 3 go into 8? 2 times. And we would talk about a remainder of how much? 2, right? 8 divided by 3 back in elementary days would have been 2 remainder 2. You guys all agree with that? Think that logic this way, okay? First things first, cube root of 2. Can the cube root of 2 be broken down any further? Well, I don't know. Get into your cube column. Where would 2 fall? Between 1 and 8. So the only possibility to check is what? 1. How many times will 1 go into 2? And if 1's the value I'm using, am I really simplifying? So can the cube root of 2 be simplified anymore? No. Okay, so listen to what I say here, all right? We're going to talk about this in the end. I'm going to do this. I'm going to put a line out here, and then I'm going to put a cube root right here, okay? I'm going to put the word whole over here. I'm going to put the word remainder over here. Okay. Whatever comes out wholly with cube roots in this case is the stuff that you could simplify out front. Stuff that you can't simplify, the remainder part is going to remain underneath your radical sign. Okay. So cube root of 2, you just told me you can't simplify that, right? There's no whole value to that. So that 2 is like a remainder. That 2 has to remain up under the cube root there. Okay. Now, this is a part where things get kind of fun, I think. All right. But my kind of fun and your kind of fun might differ. Take a look at this. What's the index here, kids? 3. What's the exponent up there?
Whoa.
13. How many times will 3 go into 13?
12.
4 times. Well, what's your remainder there, Ava? This is funny stuff, isn't it? Okay, 4 remainder what? 1. Okay, listen to what I just said. Okay. Ava said 3 will go into 13 how many whole times? So this could become an a to the 4th, but what was the remainder? Okay, so with the a's that we had up there, guys, how many whole a's could I pull out when I took 13 divided by 3? 4, but how many remained underneath here because there was a remainder part to that?
1.
Okay, let's do the next one. How many times will 3 go into b cubed? Or in other words, how many times will 3 go into 3? 1. So I could pull a b to the first out wholly. Yeah. I always said I might want to start praying when I do problems like this. What's the remainder? 3 divided by 3? 0. So I don't even need to put a b in here. I don't even need to put a b in here. Okay. So last part then is to ask yourself, how many times will 3 go into 8 right here for our variable c? And what's the remainder? So out front, what's the whole part out front? C to what power? And then what will remain for c's? Okay, your solution in the end of this, my friends, is following. A to the 4th. B to the 1st. C to the 2nd. What still remained as a root there, friends? Cube root of 2ac squared there, okay? So in this situation right here, guys, And we'll just kind of rehash this real quickly. We said to simplify stuff, you want no radicals where? Do we have any radicals in the denominator down here?
No.
Next part, no negative exponents. Are there any negative exponents sitting in here?
No.
Okay. Now this is a really tough concept, but let me ask you this. Do you understand how I broke it up into parts first? We said the cube root of 2, there's nothing I can do with that. That's why the 2 remains down here, right? Okay, just somebody fill me in on how I got the a to the 4th out here as a whole part and a to the 1st in here. 3 into 13. How many times whole? 4. And then what's the remainder here? 1. Okay. Does this idea of saying what I can wholly pull out goes out front, whatever remainder remains under the root? Does that kind of make sense? Okay, now I'm going to be honest with you. If I got my book right here and said, I'm going to read these words to you and tell you how to do it, I think if you think of it as what's whole can come out and what remains goes back under the root, I think that's a great way to remember it based on what a book would tell you and all of the language that comes with this type of stuff. Okay, simplifying radicals like this, kind of tough. Let's try that last one real quickly. Last one's a lot simpler to a point. Okay, that's what I always say. What's good about the top part, guys? Are there any radicals up here? Okay, so the top part, you're like, yay. All right, so we leave that x squared. Okay, let's talk about this next part on the bottom then. 3 into 13, how many times? This will be y to the 4th. Oh, no. Oh, no. What's the remainder going to be then? So we've got a cube root of what down here, kids? Why just a y? 1. So the assumption is the exponent for the radicand is a 1 right here. Okay? Okay, remind me again quickly, kids. Why 4? Perfect. And then why a 1 right here? Okay, let me ask this question. Are we in a good situation?